Hello, everyone, and welcome back to the AAS YouTube channel. And this is part of the great stuff. This is part of the good stuff. This is the AAS Journal Author Series, and I am very happy to have Carrie Holt with us today. Hello, Carrie.
Hello, happy to be here.
Well, I'm happy you're here too to talk about your very awesome article. Let's see. Let's start off. Carrie, what's your geolocation? Where are you at?
So I'm in Santa Barbara. I'm at Las Cumbres Observatory, but right
Ah,
outside of Santa Barbara, California.
very nice. Very nice. Is it sunny and warm there in this
Oh, it's
22nd as we record this?
it is. It's beautiful, sunny and warm. I think it's supposed to get like upper 60s, maybe 70
Oh, lovely.
today. So yeah.
Yeah, so I'm in Phoenix. We'll hit about the same today. We'll get up to about the mid 60s or so. So,
Right.
yeah, and just a factoid to put out there. So I actually did my undergraduate at Santa Barbara, so I'm
Yeah,
very
that's
familiar
awesome.
with it. Lovely.
Great place to be.
It is. And what is your position there, Carrie?
So I'm a postdoc. I'm actually an LSST Catalyst postdoctoral fellow. So my
Cool.
postdoc is focused around preparing for the Rubin Observatory.
Uh-huh. Very, very nice. And Carrie, what do you like to do for research with that fellowship?
Yeah, so one of my main interests, I like all small bodies, but especially active objects, and particularly distant comets. So comets that are coming from the outer reaches of our solar system. Yeah, from
Or other
and
solar systems, as the case may be.
right, even better. Yeah, or from other solar systems.
Very
Exactly.
cool. Very cool. And that is going to bring us to this very awesome PSJ article. It is open access. It's the open access era. People, go grab a copy for free. Go get one. Brightness behavior of distant Oort cloud comets. And Carrie, take us away.
Thank you so much. Yeah, first I want to mention I did not do this paper alone. I mentioned my co-authors. I'm part of this awesome collaboration called the LCO Outbursting Objects Key Project or the Look Project.
Mhm.
And so one of the main components of this collaboration focuses on outbursts happening in comets or really any small bodies outbursts. And then the other part of the collaboration is what makes up this paper that we're
Cool.
going to talk about.
Great shout out. Good. Okay, let's
Great.
do it. Let's go.
Great. So just to kind of set it up why we care about the brightness behavior of these distant Oort cloud comets.
Yeah.
Um, so in general, I guess I'll say when we talk about these Oort cloud comets, so we have different types of comets. We have Jupiter family comets, um, which come from the Kuiper belt, which are perturbed in from the Kuiper belt, and then we have these objects that come in from the Oort cloud,
Okay.
which is much further away. We cannot observe it directly. But the idea is that these objects um, were put into the Oort cloud soon after their creation, so that and then stored there in cold storage, so that basically these comets are thought to be the most pristine objects that we have in our solar system.
Yes.
Yeah. So since they're most pristine objects, the idea is if we can learn more about what they're made of or how these processes happen, how do they evolve, then we can connect that to the materials of the early solar system.
Cool. Okay.
And then knowing how, the solar system formed and how we got here is, one of the great
How
questions
do
that
we get
we want to
here?
know.
Yeah.
Exactly.
It'll also probably apply to other planetary systems. So,
Exactly. So that's why we think they're interesting. And a lot of the way that we one of the ways that we can kind of figure out what comets are sort of made of, besides spectroscopy, right? What's coming off of them when these comets are further away and we can't necessarily get really good spectra of them very easily. What we can do for a lot of comets is we can do optical photometry. This is one of the easiest methods to do real like astronomy in general because it can be done on smaller telescopes. You can study these fainter objects and they're more accessible. We can't just get a lot of JWST time on every single distant comet as much as I would like to.
no, probably not.
So, so the idea here is we can tell by how a comet brightens as it approaches the sun.
Okay.
So how its sort of rate of brightening you can kind of think of
Yep.
can
Sure.
tell us sort of what yeah, what ices are sublimating, what is driving that activity. So you can think of when a comet is this close to the sun and it's at this temperature, if you see, let's say, a spike in activity, then you could say, okay, what ice sublimates at this temperature? That's
Good.
probably what is coming off of this comet, right?
Cool. Good.
So
Yes.
that's like the main, that's like the broad picture. So in the past, we've used this, so I should say, yeah, so in the past, we've had uh, these studies that have shown a sort of, I'll say like a more of like a consistent brightening rate. So
Okay.
I hate to go to an equation first, but that might
Oh,
just be helpful
equations are
to
fine.
illustrate
Equations are
my
fine.
thing. So I'll go to equation two.
Okay, let's do
Uh,
that. I'm gonna skip down here a little bit there and light curves. Mhm.
yes, yeah. So historically, we've um, these studies have shown that we have this brightening rate, which here is this N number
Okay.
here. So you have how the absolute magnitude, or you can say sort of like this, the, sometimes you can kind of think about how big the comet is, or just like that standard brightness, and then how,
Okay.
and then its brightening rate is this N number. So
Right.
historically, this has been a single number, generally between 2 and 4 for long period comets.
Okay.
So, um, and we found that for dynamically new comets, uh, this is a more shallow brightening increase, so an N of 2
Right. Okay.
versus a more steep brightening rate for returning comets, an N of 4. And when I say new versus returning, I mean
No.
comets that we think might be coming towards the inner solar system for the very first time.
Right. Okay.
Yeah.
Hmm.
So that's part of the main setup for this. But those studies that happened in the past that had between 2 and 4 and only one number, all of these, most of the observations for these studies that happened at this point, like 50 years ago, they all occurred, all the observations occurred within 3 AU of the sun.
Oh
And
wow.
this is
Okay.
important because, or like most of them, that definitely within 5, because within 3 AU of the sun, that is when water ice sublimation is driving activity, which is the main activity driver in comets.
Yes. Yes.
Yeah, so the beyond that, I would imagine we all know that the activity would probably behave much differently because if water's not driving the activity, what happens beyond that? Can we use this same n equals 2 or n equals 4 to predict brightening rates as
Mm-hmm.
you've done?
Mm-hmm.
Um, right. And also historically, even for when we're predicting our own brightening, the brightening rate for predicting brightness for our future observations. So I'm doing like a telescope proposal and I want to say,
Oh
this is how
yeah.
bright my comet will be. Right now, what we use is a single
And
slope at a single n value, yeah,
yeah.
to make that prediction. And if I discover something really far away, is that gonna work out? Is that gonna be correct or not? And
That would be nice to know that, wouldn't it?
exactly. And I'm not sure if you've ever seen like a an article come out or something that they're saying like, oh, there's going to be a naked eye comet next year or like in 2 years. And like a lot of the times it doesn't actually happen. Sometimes it does, but a lot of times it doesn't. It's very hard to
It-
predict comet brightness, right? So that's one of the things that we wanted to study. So how we did that is we used LCO, which is where I am at Los Cumbres Observatory. We used their network of 1 meter telescopes.
Yep.
So um, for people who don't know, LCO it's a very cool facility. If they have telescopes all over the globe that function as like a single observatory.
Lovely. Beautiful.
Yeah, which is just super cool. So you can essentially observe an object, right, like 24/7 if you wanted to,
Yeah.
because which is very, very cool. And so what our project is trying to do is any long period comet that was discovered beyond 5 AU from the sun that is coming inbound,
Okay.
um, and will travel at least 1 AU, like has at least some distance to cover.
Uh-huh.
Um, we start observing it with LCO, and then so I add it to my little list, and then we observe it every 3 days
Oh,
for it's as long
okay.
as we can.
Okay.
And because LCO is in both hemispheres, really the only time we do not observe it is when the comet is in the sunward direction or goes behind the sun.
Okay, cool.
But other than that, we can observe it pretty awesomely,
The,
which is really unique, especially because it allows us to have very uniform observations and with like these uniform instruments all around, and it creates a really nice, these beautiful, very, very long-term light curves
yes, with great cadence. 3 days.
with excellent cadence. Yeah. So I love going to talks and showing these light curves and stuff too, because everybody's like, wow, that's so crazy. Um, so this paper is the first 3 years of data from this project.
Okay.
So fortunately, we are still ongoing. So we are about to wrap up another 18 months past that first 3 years. And we just got approved for another, I think 18 months or maybe another year. When LSST comes online, which we could talk about later, things are going to shift a little bit, right?
A little bit.
Yeah. Yeah. So that's basically our sample. So if you want to scroll down to figure one.
Sure, let's go in figure one. These are the LPCs monitor.
Yeah, these are the comets that are part of our sample. So we've observed more than that, but these are the ones that made enough heliocentric distance coverage that we can characterize for this paper.
Okay, very cool.
So this includes like 21 objects, but right now we're observing like over 40. So
nice. Okay,
yeah,
good. Okay, so I just wanted to touch that one. Data collection, else look LPC observations. Here we go.
yes, yeah. So this just kind of shows the sort of how many observations and the range that we can get with LCO and with this collaboration. So here you have each of the comets here on the left, and then you can see the pre-perihelion range of observations and the post-perihelion range of observations. So every black dot is an observation,
cool.
And then you can see the whole range in the blue and the gray bars.
Yeah, very nice.
Yeah, so this can just show you some of these objects going all the way from like I'll say T4 as an example, but can go all the way from like 7 AU to almost 1 AU, which is crazy.
Yeah,
C22. Yeah, so it's
really close. So is this one here.
Yeah.
2020.
And so the range that we can do is pretty amazing. And this takes years, right? This takes years to because they still travel slowly enough. So it takes a while. So
like this
really
one.
awesome data set.
Perihelion of greater than 6 AU. So yeah, that's going to take a little while. Two of the objects have asterisks, C2103, and what do the asterisks mean?
Yes, so these asterisks mean that we had to stop observing them because those objects either fully or partially disintegrated.
Okay.
Which is honestly to be expected. I mean, those are some of the objects that came the closest to the sun. So there's that, and with the percentage of objects that we're observing, like for about 2 to disintegrate makes sense.
10%. Yeah.
Mm-hmm.
Plus, it's interesting to see how they disintegrate. Anyway, that also tells you about the volatiles, right?
Right. Exactly. Fortunately, a lot of times, they disintegrate on the other side of the sun where we can't observe them while it's happening. But we did our best. I have some observations of dust balls, so that's nice.
Okay. Very nice. Great observations. Okay.
Cool. So we did a few different things with these observations. So I'll really, we'll do like 3 main things. The biggest thing that we wanted to do was measure this brightening rate, measure this N value for all of these.
Yes.
So that was one of the first things we did. And then we also did, we looked at the evolution of the colors. So we used the G and R band filter.
Yes.
And for comets, G and R, and the G minus R color is interesting because the G band has a lot of emission lines that we're seeing in comets, so these gas emissions, whereas the R band is more devoid of these gas emissions. So you can kind of do G minus R as like a loose kind of way to do some sort of gas to dust, or proxy sort of thing.
Yes, proximate.
Yeah.
Okay. And
so we do that, and then we also tried to look at the coma morphology. Granted, we can only do these for objects that come close, but this idea is if we have a gas image with the G and a dust image with the R, we could kind of subtract them and get this sort of gas image and see if that works as a method, first of all, because it is um, that would be much easier to do than getting these narrowband comet filters, which we use a lot
Mm-hmm.
um, for these sorts of studies. But you have to be closer. But they're more rare. You can't find them on every telescope
Yeah.
and those things.
Cool.
Um, yeah.
Okay, I'm with you.
So that's where we're at. We also wanted to look at the what we call the dynamical age of these objects.
Okay.
So, which right now to know if an object is new or returning, or like how pristine this comet might be, it's really done with dynamical models. So they, which I do not personally do, but other people's dynamical models, they trace the orbit backwards and can see like what is the original semi-major axis, which can then give us an idea of how new an object is.
Okay. Mm-hmm. Mm-hmm.
Yeah. Um, but different sources use different methods, and it's really hard to do. You need a lot of time of observation. So we looked into that as well.
Okay. Cool.
Um, so with that, let's go into some of our results. Let's see.
Okay.
Yeah, so I talked about the n value.
Yeah.
Yeah, the Comets morphology. Okay, so let's talk about I'll talk about that dynamical age. Or actually, no, we're gonna skip that a little bit. Cool. So we can go into our actual fitting of the n values, which
Okay.
is our main figures, starting with figure 3.
Okay. There's our equations again. Those are the comet morphologies we just talked about, activity indices, dynamical ages, activities, more colors.
Yeah.
And figure 3 we want?
Yes.
Okay, let's get some summary. I'm going to zoom out so we get the whole thing here, and we'll
Yeah, great.
as need be.
Yes. Great. If anybody wants to go back, like in general, the figure that we skipped over talks about why I chose this specific way of doing dynamical age, which is it basically just chose this one source because it made sense, and you can read more about that, but it's a little tricky to get into, so we're gonna
We'll concentrate on the
skip over
figure.
it for now.
Okay.
So these are fits. So what we found when we actually
Okay.
started making these fits, first of all, in general, comets do what they want. Predicting comet behavior, you know, some people wonder why we try, but it's obviously it's something that we want to do, and they have similar things.
Practice makes
So
okay.
yeah. So obviously what we found is that in
Wow.
a lot of times a single
Yeah.
n value does not work for pretty much all of these if you go across a large enough heliocentric distance.
Yeah.
Um, some of these, so like this bottom left one, the range wasn't long enough to really even get one. So the bottom right, the C2021A1, this is an object that disintegrated. So you
Okay.
can kind of see that started its
Yeah.
being as it's disintegrating.
Right.
Um,
Which
yeah.
fragment are we picking up? Okay.
Mhm. Um, yeah, so if you want to scroll down a little bit more, I can to the next set.
Okay, just getting the sense. Yeah, they're
Yeah.
all
So we have so just to go into this figure a little bit, right? So you have the heliocentric distance, so how far away this comet is from the sun, that's the x-axis. So you have pre-perihelion on the left, post-perihelion on the right. And then
yes.
you have what we call this like heliocentric magnitude, which is essentially how bright the object is, but corrected for all other geometry factors except for how close it is to the sun.
Good. Okay.
Um,
Yeah, and those n values go all over the place from 1.3 to
mhm,
12.
right,
Okay.
exactly.
So much for the idea of
And
n.
so if you scroll down to the next page, you can see another trend that we see.
Okay, let's go down.
Yeah.
Oops, let's zoom out again. So
So
this is
not only, yeah, so not only do we see that a single n value does not work with comets at these distances and across these large heliocentric distance ranges, we also see that for most of them, they start further from the sun at a steeper brightening rate or a higher n value that then shallows out to a lower n value as it approaches the sun.
okay. Okay.
So you can see a lot of these, right? They start steep and then they kind of shallow out as they approach the sun,
Yeah,
as they
for
go from
5.6 to 2.5 as you get a little farther, 7 to 3.6. Yes.
right, exactly. Yeah, so that's also interesting because we had imagined that we knew that especially for dynamically new comets, you had this we studies that occurred near the sun, right? We said they had a very shallow brightening rate of like 2 compared to returning comets.
Uh-huh.
So that was always hypothesized that they must have a steeper brightening rate further from the sun. And this is what we're able to see here now. So that's really cool.
This one's kind of curious. We got an N value of 0 here.
Yes. So
What?
when you have in this case what an in value of yeah, 0 essentially means that
It flashes the
intrinsically
photon.
is not brightening. Actually, I think in this case because it's a um in helio where you just the reflected light, you would expect it to at least
Oh,
be closer to like into. So it's actually almost like decreasing in intrinsic brightness a little
yeah,
bit.
exactly. Exactly. So
Hmm.
if N was negative, it'd be getting dimmer.
Exactly. And we also see like in this the bottom right comet here,
Uh-huh.
C2022A2,
Uh-huh.
for some comets, we see this sort of this jump, right? This surge in
Yeah.
brightening.
Mm-hmm. Mm-hmm.
And then and in some other
Mm.
ones we see sort of like evidence that there has to be some more surge, like the two different they don't line up very well. So we know
Yeah.
that some of these kind of you can see this sort of surge happening. Yeah, like between these two and T4, like we know that
Yes.
might not connect directly here.
Right. Because at some point stuff will sublimate and it will start
Mhm.
outgassing. Yep. Yep. Yep.
Yeah.
Very cool.
So
Okay.
those are our big individual takeaways. So then if you go to the I guess figure 6, so you can scroll through and see our last set, but they look similar. So here, this figure 6 is kind of putting that all together for all of our objects.
Yay.
So here we're showing the activity index and so that brightening rate
Yes.
against heliocentric distance. So
Uh,
we basically separated at what heliocentric distance is the brightening rate occurring.
okay.
And you can see for the most part,
Okay.
just like we could see it, it's not only true for the individual comet that it starts out with a steeper brightening rate that then shallows out. For the whole population, further from the sun, it is steeper. Closer to the sun, it is more shallow.
Oh, yes. Yes. Yeah.
And at
Cool.
least pre-perihelion. Post-perihelion is less certain. Part
Yeah.
of that is because we don't have as many observations post-perihelion because this is only the first 3 years, but that's something that we are looking forward to as our observations continue, is being able to do a better pre versus post-perihelion analysis. But
Mm-hmm.
you can also, one of the other interesting things with this is that within like 3 of the sun, the brightening rates being within 5 to 3 being within 2 to 4
Yeah.
is still
Yeah.
consistent. So this isn't negating previous.
Previous work. Yes.
No, not at all. This is just like expanding on it. And I think one of the interesting things here too is that basically these objects that become more shallow right now, you can see post perihelion
Mm-hmm.
they don't aren't necessarily as shallow. Again, part of that is because we can't say too many certain things. Again, we don't have as many observations. Some of them weren't even observed at this like point, so more work to be done here. But that would be another cool result to say, oh, it can get shallow, but when it leaves the sun, it's about the same. It doesn't have the same trend post perihelion, which would be cool. But
Yeah,
that is
definitely. Okay.
TBD.
Okay, we'll come back to that point. Okay.
Yeah. And kind of to emphasize that a little bit more of what we have so far is the next figure, figure 7,
And go down.
shows
Figure
um
7. Oh yeah. Mm-hmm.
yep. So this shows the sort of range, um the range of brightening rates that you have pre-perihelion or pre-Q, that green slope versus post-perihelion. Right. So you have a much broader distribution pre-perihelion than post-perihelion.
Right. Yes. Okay.
Yes.
Okay. Very good. And activity indexes. Yep. Mm-hmm.
Yeah.
I'm with you. Good. Okay.
Great. And so then we kind of go into what, how does this look versus for new versus returning comets? Because like we said, a new comet is we've known to have a more shallow brightening rate compared to a returning comet.
Uh-huh.
And so we want to know, is this true? Because this would also be helpful if we could have a observational diagnostic to tell if a comet is new versus returning. If we want to, send a spacecraft to the most pristine object, the
Yeah.
earlier we can find out that it's new, the better, compared to if we had to wait however long before dynamical models can be good enough. Like if there's enough observations to have a good dynamical model.
Right. To reduce the uncertainties on where those positions may be at some future point. Correct. Yes.
Right. So,
Right.
um,
Okay.
so we only when we use this, the variable that is currently being used for if a comet is new versus returning, which is this inverse of the semi-major original semi-major axis, we only have um,
Oh,
a few returning comets. Most of them are considered new, but this sort of what makes a comet new versus returning, and comets don't, an object that is new isn't necessarily coming directly from the Oort cloud. It comes closer and closer each time, and that's also a little tricky. So the new versus returning idea is hard within itself if you're talking about dynamically and what that might mean.
yes.
Um, yeah, so it is a whole like can of worms that we can go into, but we're going to skip over that can of worms for now. But I'll at
Okay.
least show you what we have if we assume that this new versus returning cutoff that we made is correct. So
Okay.
which is what has been used in previous studies.
Okay.
So the next figure is figure 8.
Get 8, and this is new and returning.
Yeah.
Uh,
So the main thing here is that we do not find a difference in this activity index between new versus returning. Um,
True. The peaks are pretty close.
and granted, there's much fewer returning comets. Like there's only
Yeah.
3 pre-perihelion that have observations compared to um, uh, these new comets. So again, I wouldn't necessarily say it's small numbers. I wouldn't go too far, but that's what we don't have enough to tell a difference based on this activity index number for now.
It's a work in progress.
It is a work in progress. Obviously, the more objects that we have and the longer baselines that we have,
Yes.
the more we'll be able to say, which we're continuing to do with Look, and then yeah, when uh, Cumbres Observatory comes online, we should be able to do even more. So, but
Mm-hmm.
that's what we found for
Okay.
now.
Good.
Um,
With you.
we also found, if you scroll down to the next couple figures,
Sure. Let's take a look at figure 9.
yeah,
About
this is a messy figure, but I need to find a way to show.
Yep.
Essentially, we use this AF row value um, as a way to proxy like dust production, sort of. So this is just goes to show that we don't see a difference
Okay.
in activity values, like the rates, but also just not even values for new versus returning comets.
Yeah, it's kind of a scatter plot.
Yeah.
A
Um,
little bit less so post, right? Post J.
yes. Yeah. And a lot of this is because, yeah, the returning comets get closer to the sun, which is another thing that like we'll talk about later.
Okay.
Um, but this figure on the right also talks is another way to say this. We looked at the color between new versus returning.
Okay.
This figure on figure 10.
Oh, sorry. Gonna say.
Again.
Oh, here we go. Color. Huh, thank you.
Yeah, yeah, that's just right there. And we again, few objects, but we don't see a difference in color in the average color here. Later, I'll show the sort of evolution of color is the one thing that we do find to be
That's
different.
nice to see. Okay. Okay.
But this is
Yeah.
just saying that we don't really see a difference. So that our takeaway for our sample that is small, we don't have a lot of objects in the returning category. We don't see many differences between new and returning. That's the takeaway there.
Yeah. That is a work in progress. Good. It's good.
So,
It's good.
thanks. So then we'll talk about the color evolution.
Yes.
So that's the next figure.
go down to, okay, so let's zoom out. Okay, here we go. G minus R versus distance. Here we go. Okay.
Yep. So we found that the six objects that came within 3U of the sun, these are the objects that showed a color change when they approached the sun.
Okay.
And this makes sense because
Hmm.
you have when you have water, gas production is increasing near the sun. You also just have, increased gas emission. And so
Right.
you would expect that gas to dust ratio to shift, potentially, or just have the G band to be brighter, that ratio to shift.
Hmm.
Um,
Okay.
so that's kind of what we see here in these six. So you can see, yep, they start all of them decrease, have a bluer color near the sun, which
Yes.
means like that there's more in the G band compared to R band, the ratio of it.
Good, good. And some of them you got pre and post. Good.
Yes. And yeah, you can see it kind of coming back out of it for some of these
Right,
as
right.
well.
You can imagine smooth curve there. A little more imagination on a smooth curve there, but okay.
Yeah. Um, so putting it together, if you go to the next figure,
Okay.
these objects, that's figure 12. Yep.
12. Okay, let's go. Color evolution.
Yeah.
No.
So another takeaway, again, these are six objects. So I'm just going to start with that. There's six objects,
That's
very
fine.
few numbers, but we are showing this thing that we found with six objects, and we'll see if that holds once we add more or if it breaks down. But what we found was that for our returning comets, they changed color closer to the sun than our new comets.
Yes. Yes. Okay.
So this could be
They're
for so one of the ideas is maybe um, returning comets are more dusty, so there needs to be more gas to sort of overpower its dustiness, or maybe there's more deeply buried volatiles, like
yes.
so the radiation from the sun needs to penetrate deeper layers before the ice sublimates, and that might take a little bit longer.
Right.
So that's another idea. So this this is an interesting,
Yeah, it's intriguing. Hmm.
yeah, um, and sort of
But it makes sense.
going into why this happens and trying to better model the coma, because in theory we can probably play around with this a little bit with as far as um, what we think some of these sublimation models can do with the color change and how that would relate.
Uh-huh.
So that is like a future project that we're hoping to work on, is to try to better understand how this color change happens. Does the rate of color change? What does that mean? Because in general, you can see the rate almost looks the same between new and returning here. It's just like the returning is closer to the sun when it happens. It just is a
Yes.
little delayed.
Yes. But the
Um,
morphology coming in and even out is about the same. It's just shifted.
exactly. Exactly. It's just shifted. So yeah, so trying to better understand that is definitely a future goal. But for now, we will speculate and just share our results.
It's mystery. Mysteries like to be solved. Okay.
Exactly. It is a cool result to see for sure. And especially because we've known that um it's not surprising that comets change colors as they approach the sun. That's not surprising, but there's hasn't been a lot of um big data sets that kind of really show this all coming together.
Huh. Uh-huh. Well,
So that's
congrats
nice.
on this one. Good.
Thanks. And then finally, we looked at the coma morphology.
Correct.
So
It's number
if
three.
you want to scroll down to figure 13.
Let's take a look at 13, and here's some comas. Woo.
Cool. Yeah. So I'll try to explain this a little bit and then we can get into the other ones that look very similar. So the here you have the left is a G image, and then so the bottom row is just an enhanced version of the top. So you basically removing the azimuthal median
Okay.
to show the enhancement. So
Okay.
the the on the left we have a G image, and then you have the R, and then we scale the R image um,
Okay.
uh, to get a dust color, and then we subtract it to get a what we call like this gas image kind of. So we
Yes.
yes. So you can see when we do that, we're able to get these um, really nice jets coming out of this comet.
And just to be clear, that 0.61 multiplier is chosen for a visualization purpose. There's no actual physics in that 0.61.
No, so it was chosen using like a by eye like situation, basically chosen to when we see that the tail is because
Ah,
we imagine the dust the dust the tail is has a lot of dust in it. So when we see that tail go away, that's kind of when we stop
gotcha.
our scaling. But
Makes
that actual number can then be used as I mean it is the you can think of it as the dust color, really.
right. Okay. Okay. I'm cool. I'm
So a
with
lot of times
you.
this number will then equate if you put it back into the equation, a lot of times that color will equal the color of the object before it changed colors. So
Ah,
that's the dust color
gotcha.
is that.
Cool. So there's
We didn't, but it does relate to dust color, which is cool because one of these objects has a weird dust color that we don't exactly know why.
okay.
So
Thank you.
yeah, so and we've been able, at least for this one too, in their the paper by Tim Lister in 2021, who had a year one summary of the look collaboration. He
Yes.
showed a figure very similar to this and included an image using a CN filter, and
Okay.
it looks very similar. So that's really promising that we
Um,
can use this as a method if we don't have access to um, the narrowband comet filters.
Fair. Okay. I'm with you. Good. I learned something.
Cool. So
Yeah.
So, so this one we can obviously see some jets. So
Sure.
we found that the only the six objects that had this sort of color change had enough gas to create a gas image, like a true gas image.
Yeah.
So we could only do that for those six objects that we just showed the color for.
Yes.
But I will show you what we found there. So we scroll down to the next
Yes.
ones.
2021 A1. And here we got two of them. So I'm going to, three of them. So I'm going to zoom out to get a global.
Yeah.
Okay.
So here are a few more. And you can maybe see some faint asymmetries here, but they're very faint
Mm.
too. I'm not going to put a strong
A
confidence,
little bit.
at least in the gas image, I mean.
Yeah.
Yeah.
Uh-huh.
But I tried to like highlight them where I felt that I saw them. Definitely in this bottom image, I don't see any at all.
Right. That looks pretty uniform to me. Okay.
Mhm.
All right.
Um, and then if you scroll to the next page, you can see our last two,
Okay.
where again, this top image, we don't really see super asymmetries, maybe a little bit in the gas image. And then this bottom one, we definitely do.
Yikes. Absolutely. Hmm.
Yeah. And so one of the interesting things
Oh,
here is that the two objects that have
okay.
the strongest asymmetries, so this last one, 2022 E3, and then that first one that I showed,
Yes.
those are our two returning comets.
Bingo.
Yeah.
Uh,
So
so this one, let's
which
look at this one again. Yeah. Okay.
yeah.
Okay.
And so
Okay.
this is interesting because there is this idea that a returning comet, basically on a comet's like as a during a comet's initial passages, maybe it will have acquired maybe it's part of like a dust mantle, or will have a more irregularly like covered surface, so that there will be more jets on a next passage. That is a theory that people have been thinking about and looking into. So this would maybe explain that. However, I said this is a big thing. However, those are also the two objects that are closest to the Earth and to the Sun at time of
Um,
observations. So definitely closer to the sun. So I think I have a table in here that, yeah, the right below that image is a
yeah.
table that
Comet.
kind of shows
Hmm.
where
Okay.
these objects are. So A1, the top one and the bottom one are our two returning comets. So these
Mhm.
are the closest to the sun, um,
Yeah.
and pretty close to the Earth. I mean, there is the C-22 T4 was also close to the Earth at times of observation. So in theory, you might be able to, we should have maybe seen something there, but nonetheless, those are very strong jets in the returning comets. So again, we're just going to need more observations to know if this is a true phenomenon or not. Oh, and then yeah, that what you circled just there, the dust color, that's I
Uh-huh.
took we took that scale factor and
Uh-huh.
then
Yes.
turned it into dust color. You
Yes.
can see most of these are around like this 0.5, 0.55, which is what
Yeah.
the average colors are, except for this bottom one, which is
Ah,
very red
all right.
dust color,
Ah.
which
Mhm.
not exactly sure why that is. It could have to do with the size of the dust grains. There could maybe be some contamination from some um, gas
Other.
in the R band in that particular case. It's something that to look into more, but it's interesting.
uh, Outlier. Interesting. Okay.
Hmm.
Mm.
Yeah,
Okay.
yeah. And so I think this our last figure here on the left too is just I wanted to show that we found that the C-2021 A1, which was one of our disintegrating comets, that had the bluest color of the whole population once it as it disintegrated, it was the most blue.
Okay. Hmm.
Um, and then this image here is a G-band image of another comet that disintegrated. We weren't able to observe it as close to its disintegration time because it went behind the sun as we could A1, but you can kind of see very roughly. It depends on people's contrast, I guess.
Yeah.
But we were able to measure it. There's like a slight fuzzy blob, and we found that this fuzzy blob it was only seen in the G band, so it had an
Oh,
extremely blue color as well.
yeah.
So that's also interesting.
Wow. I think like all good works, there's more questions than answers. Very cool. Very
Thanks.
cool. Okay,
Yeah.
and then we'll get into eventually Ruben
Yes.
O'Brien.
Right. So this is one of the things that we had with the look collaboration is sort of thinking, especially with this 3-day cadence, which is going to be about the cadence of the Rubin Observatory,
Yes. Hmm.
seeing what sort of science are we able to do once Rubin comes online? What sort of tools do we need to build to better to quickly analyze some of these objects as they're coming in? Um, so we have a small um, sample
Yes.
right now,
Yes.
but it will increase by
Oh, a few
a
orders of
lot.
magnitude.
A lot. However, the main for us for these distance comets, it's less about how many because more a lot will be discovered, but for us, it's how we can discover them more far away, so we can cover a longer baseline. Because if you think about it, we have these comets that are coming in there's not going to be more necessarily like bright comets, right? We've discovered them bright. It's just we'll be able to
It's gonna be the
discover them as
huge.
they're
Yeah.
further away.
Uh-huh.
Yes. And then maybe there'll be some overall fainter ones, which will be interesting. That would be interesting. I don't know what that necessarily looks like right now. So I'm really excited for Room Observatory to come online and us to get these populations. One of the things that will be different and interesting that I'm hoping to test soon is um, LSST will not be doing simultaneous color observations. So
Okay.
these sort of
Okay.
the color analysis that we just did showing that evolution
Mm-hmm.
might be trickier to do. So that's one of the tests that I'm also working on to see if if the cadence that is currently being set up, if we can still capture these color
That.
changes, or
Right.
if we or not, or and seeing that.
I mean,
So that's
presumably,
interesting.
yeah, I mean, presumably it's a little easier to get time on LCO scopes than it will be Rubin. So in some sense, LCO is a follow-up to
Absolutely.
right? Yeah.
Yeah, that's one of the a personal, like not personal, but one of the collaboration projects for a solar system science collaboration that me and my postdoc advisor Tim Lister are working on is trying to better organize the follow-up
Yes.
observations
Yeah.
for LSST. Because yeah, exactly, LCO is a perfect spot for that. And that's the thing too, like if LSST can't get the sort of color information that we want, then that's even more motivation for us to, apply for telescope time to get it ourselves if we need it.
Exactly.
So that is a test we need to do. So
Very
yeah,
well. Carrie, I want to thank you so much for walking us through your very awesome article. Beautiful.
thank you for having me.
Beautiful, beautiful. Okay, very cool. Um, and you mentioned it a couple times there, particularly toward the end. Um, but let me push on it just to get some other directions going. And where do you think we go from here, given the published article?
Yeah.
There's clearly more observations coming between Rubin and that. Are there different theoretical models that could be investigated, perhaps distinguishing better between new and old returning comets? Is there laboratory astrophysics works that needs to be done on, if you are going to do spectra on those comets, some of the lines that may be coming off there? I don't know. But just sort of next steps, where do you think we go over the next couple of years?
Yeah, so for my interest having to do with the evolution of these objects in all the ways that we can understand them. So one of the more immediate follow-up things that I'm working on now, which should be coming out soon, is we see this brightening, the change in brightening rate, right? And that means that the models that we've been using are not necessarily the best models to use when it comes to predicting brightness behavior,
Got it.
predicting predicting discovery distances for Rubin either, right? So
Hmm.
I'm working on uh, a model, like a quantitative model for that brightening rate that we can then use to
Cool.
characterize the brightest behavior in a different way that has a heliocentric dependency.
Right. They can vary.
Exactly.
Cool.
So because those fits I did, just piecewise by, and that's not really good when you're looking at LSST and you have so many comets, right? So
Got it.
that's the immediate next things. Yeah,
Cool.
I want to do like I said, the sort of color change and having a model for how that works and how that happens and the different things that would go into that potentially or not go into it. Is the dust to gas ratio changing, or is it just a factor of the G factors and scale lengths and all these other things that
Yeah.
go into sublimation models?
Yeah.
So looking into that, and then yeah, obviously when Rubin comes online, we got a whole bunch of more objects to look through.
I predict a busy time coming.
Yes, indeed. I'm looking forward to it.
Very cool. Very cool. Carrie, thank you so much for walking us through your very lovely article and long-term work comments.
Awesome. Thank you so much for having me. I enjoyed it.
And that will do, everyone. And I hope this made your astronomy day, your Oort Comet astronomy day, just a little bit better. And we will see you on the next one. Bye-bye.